The Lorentz coordinate transformation. The Lorentz transformation equations show how the coordinates of two different reference frames that move at a constant velocity are related to each other. By the way, if you like this video, don't forget to like and subscribe to this channel. Activate the bell. It's very important for the continuity of this channel. Our first question is this. When an event occurs at the point P at time t as observed in a frame of reference S, what are the coordinates and time of the event as observed in the second frame S moving relative to S with constant velocity v in the x direction? Let's consider two inertial reference systems, S and S', moving with respect to each other at a velocity v. Let's suppose that at time equals 0 in S, we have t prime equals 0 in S prime, and that the origin of both coordinate systems coincides at that time. Thus, the distance x from S to event P as seen in S is v times t plus x prime. We can solve this equation for x prime. But we know that x prime as measured by S prime will be contracted by the Lorentz factor, and we can rewrite this equation as follows. This is the relativistic transformation of the x-coordinate of space from S to S prime. This equation relates the position of the event P as seen in S prime. Sometimes we observe the position in the moving frame S prime, and we need the value of x in the stationary frame or frame S. To get the equation that relates the position of the event P as seen in S, we can interchange primed and unprimed quantities and reversing the sign of the relative velocity v. If the S prime frame has a positive velocity relative to an observer in the S frame, then the S frame has negative velocity relative to an observer in the S prime frame. This equation is also known as the inverse Lorentz transformation for x-coordinate. We can obtain the equation for the time coordinate by isolating the time prime in the equation and eliminating x prime by using the Lorentz transformation for x prime that we just found. We have assumed that there is no relate motion between the frames in the y or z directions. If this is true, then there will be no relativistic change in these directions either. Pay attention. We can summarize these equations in the following table. Let's see how it works. Pay attention in this question. First, let's calculate the value of the Lorentz factor. This question is a straightforward application of the Lorentz formulas to find the coordinates of the event according to the rocket's reference frame. Pay attention. Let's see another question. First, let's calculate the value of the Lorentz factor again. This is a straightforward application of the Lorentz formulas to find the coordinates of the event according to the electron's frame. It's done. Sometimes we'll be interested in the difference in coordinates of a pair of events. So for events 1 and 2, we can rewrite the Lorentz transformations in terms of any pair of events 1 and 2 with spatial and temporal separations. Pay attention. Let's see how it works. We seek for intervals between two events, which we shall get by transforming the given S-frame to the frame S'. Because we are considering a pair of events, we choose transformation equations from the last table. We choose frame S to be stationary and the frame S' to be moving with positive velocity. From the question, we can see that the interval of length is 30 meters and the interval of time is 0.1 microseconds. We now find the Lorentz factor. We now replace these values into the equations to calculate the interval of length and the time interval. Let's see another example. This traveled by the light pulse from emission to reception as seen from each frame is in figure below. Event 1 is the emission of the light pulse. Event 2 is the arrival of the light pulse at the front of the rocket. Clearly, the distance separating the emission and reception of the light pulse according to an observer, as seen from S', is the length of the rocket, 630 meters. This distance is covered at the speed of light, and so the time between emission and arrival is given as follows. To find the distance and the time interval separating the emission and reception of the light pulse according to an observer, as seen from S, we use the Lorentz transformation equations, pairs of events. Pay attention.